Let's look at another problem involving an ideal gas. And in this problem, I'm going to introduce through some mini lessons the concept of enthalpy and specific heats, which will be required to solve this problem. 2 kilograms of oxygen fills the cylinder of a piston cylinder assembly. The initial volume and pressure are 2 cubic meters and 1 bar respectively. Heat transfer to the oxygen occurs at constant pressure until the volume is doubled. Determine the heat transfer for the process in kilojoules, assuming the specific heat ratio is constant at K equals 1.35. Kinetic and potential energy effects can be ignored. Let's lay out our storyboard. We have a piston cylinder assembly containing oxygen, and I've drawn the system boundary around the oxygen molecules. The oxygen is heated and produces work. Let's see what the given data is. At state 1, we know the pressure is 1 bar, the volume is 2 cubic meters, and then we have a mass of 2 kilograms of oxygen. For state 2, it's a constant pressure process, so P2 is equal to P1. And the volume of state 2 is double the volume of V1. Well, the volume at state 1 was 2 cubic meters, so the volume at state 2 will be 4 cubic meters. The process can be described as a heating process. It's also undergone at constant pressure, and the ratio of specific heats for this process is K equals 1.35, and I'm going to introduce this in a little mini lesson shortly. While we're at it, we grab the molecular weight for oxygen, which is 32. Let's plot this process on a PV diagram. Now, as you'll recall, on a PV diagram out in the gaseous or vapor region, that temperatures go down to the right. And this gaseous state is far gone from the vapor dome. So you'll notice the vapor dome doesn't even show up on this drawing. But we know that state 1 has a volume of 2 cubic meters and has a pressure of 1 bar. And its temperature line would be shown right here. We don't know what that is, but we'll call that T1. This is a constant pressure process. So it's going to stay on this horizontal pressure line of 1 bar until it gets to a volume of 4 cubic meters. And the constant temperature line that represents the final state's temperature would be coming down to the right, going through state 2. We'll model this as a closed system, of course, and we'll ignore any changes in kinetic and potential energy. The process is a constant pressure process, and we're going to assume constant specific heats for this process. And we're doing that because K is given as a constant. And as you'll see shortly, K is simply the ratio of two constant specific heats. So if the ratio of is constant, then the specific heats are constant. So anytime we see a K value, we'll know that we can use constant specific heats to solve the problem. And I'll talk about that shortly. And of course, we were given that the oxygen behaves as an ideal gas. And we want to find the amount of energy transferred into the system via heat transfer. Let's digress from our problem here and have a couple of short lessons which we're going to need to solve this problem. Let's introduce the concept of enthalpy, and we'll do so by considering a closed system undergoing a constant pressure process, which is exactly what we're dealing with in this problem. So if we were to write a first law energy balance, ignoring kinetic and potential energy effects, we would have that Q is delta U plus W. And we know that work done by a constant pressure process, or any process, is given by the integral of P to V. But for a constant pressure process, that's simply the pressure times the change in volume. So we can rewrite the energy balance, substituting P delta V for work. And we have Q is delta U plus P delta V. Well, let's expand these terms of delta. So what is delta U? Well, it's just U at the final state minus U at the initial state. And P delta V is just P times the quantity, the volume at the final state minus the volume at the initial state. Let's rearrange and put all our final terms together and all of our initial terms together. And we get Q is U plus PV final minus U plus PV initial. Well, going back to our delta notation, we can say, well, then Q is delta, or the change in U plus PV. It would be U plus PV final minus U plus PV initial. Let's, for convenience, define a term. Let's call it enthalpy and designate it by the letter H. And we'll say that H is equal to U plus PV. Now that we've introduced the concept of enthalpy, let's introduce the concept of specific heats for vapors and gases. There are two of them, C sub V and C sub P. Let's define them as follows. C sub V is defined as the partial derivative of internal energy with respect to temperature at constant specific volume. C sub P is the partial derivative of enthalpy with respect to temperature at constant pressure. So we will find that specific heats for vapors and gases vary with temperature. We can go into tables and for many common gases find the value of C sub P and C sub V, and for the specific heat ratio K, we can find values in tables as a function of temperature. But for many processes, we can assume that specific heats are constant. And we do that by maybe using an average value of the specific heat for the temperature range of the process. Certainly, if delta T is less than 200 degrees C, it's very easy to assume that the specific heats are constant. And for some gases, you can have a much larger temperature range than 200 C and still assume that it's constant. Now, when we assume constant specific heats, we find that they are very helpful in calculating the change in internal energy and the change in enthalpy, and we can calculate these without table values. So we can say that delta U is C sub V times mass times delta T, and delta H is C sub P times the mass times delta T. Now we mentioned earlier this value of K in the problem statement, and K is just the ratio of specific heats. It's C sub P over C sub V. Sometimes you'll see that ratio given as a Greek gamma instead of K, but I like to use K. And we will find out, I'm not going to derive this, but when we have an ideal gas, there's a strong relationship between K and R. We can calculate a value of C sub P as Kr over K minus 1, or we can calculate C sub V for an ideal gas is the gas constant R over K minus 1. Let's summarize what we've learned about specific heats for gases. And let's particularly look at this problem where we have a constant pressure process, which we call an isobaric process. We know that by ignoring kinetic and potential energy effects, that delta U is Q minus W. We also know that for an isobaric process, W is P delta V. So we can solve for the heat transfer during a process like this. It's simply delta U plus P delta V. But we introduce the concept of enthalpy, and we'll recognize that U plus PV is enthalpy, and so delta U plus delta PV is delta H. So Q is equal to delta H. Now, we always can assume variable specific heats, and that's where we'll get values for internal energy or enthalpy out of tables. So in the case of variable specific heats, we can calculate delta H as the mass times the change in specific enthalpy, which are table values. We would get H2 and H1 from a table. On the other hand, if we're going to assume that specific heats are constant over the temperature range of the process, then we can calculate delta H as simply m, the mass, times C sub P times delta T. So let's get back to our problem now that we've introduced some concepts for enthalpy and specific heats. And I'm going to solve this problem two different ways. So let's look at the first method. We can write an energy balance. Q is delta U plus W. And we can solve for delta U and W independently, where delta U for process 1, 2 is the mass times the C sub V times T2 minus T1. And I'm invoking constant specific heats here because I was given a value of K. And recall that K is C sub P over C sub V. So if K is constant, then C sub P and C sub V are constant, and I can therefore assume constant specific heats for this process, and I can use that to calculate delta U. The work term for a constant pressure process will simply be the pressure times the final volume minus the initial volume. Now, in order to solve this problem, I'm going to need T1 and T2. I can get them from the ideal gas law. T1 is P1 V1 over MR, and I know all of these values. The pressure is 1 bar. The initial volume is 2 cubic meters. I have an energy conversion here of 1 bar cubic meter is equivalent to 100 kilojoules. The mass of the system is 2 kilograms. The gas constant is 8.314 divided by the molecular weight of 32, and that having units of kilojoules per kilogram K. And I calculate that T1 is 384.9 Kelvin. We can do the same for T2. It's just P2 V2 over MR. And we can go through the same calculations, but the only term in this expression that is different than the term in our state 1 expression is that the volume has doubled. Okay, so essentially, since the volume doubled, and that's the only thing that changed in our expression for T2, then the temperature is doubled. And we can see that that's exactly what the result of this computation is, that T2 is exactly 2 times T1. Well, now that we know that, I'll show you that there was actually another way to calculate T2. We know in a constant pressure process, P2 is P1. So it's MR T1 over V1 is MR T2 over V2. But MR is a constant, so we can exclude it from this equality. And I'm left with T1 over V1 is T2 over V2. Or the final temperature is T2 times T1 times V2 over V1. Well, remember that V2 over V1 is 2 because the volume doubled during this process. And so I get that, once again, that T2 is double T1, or 2 times 384.9 Kelvin. And once again, I get T2 is 769.8 Kelvin. So now I can go back and solve my expression for Q using the energy balance. We had Q is delta U plus W, and delta U is M C sub V delta T. We just calculated T2 and T1, plus the work term of P times V2 minus V1. Now I need the value of C sub V. And you may recall this expression that was given in my little mini lesson, that C sub V is the gas constant R divided by K minus 1. We have all the information we need to calculate C sub V. The gas constant is 8.314 divided by the molecular weight of 32, that quotient having units of kilojoules per kilogram K. Value of K was given as 1.35. So C sub V is 0.742 kilojoules per kilogram K. So now I have everything I need to solve for the heat transfer. The change in internal energy is simply given as the mass times C sub V times the change in temperature. And the work term is the pressure times the change in volume. And when I add all of these together, I get the heat transfer Q is 771.2 kilojoules. Let's look at a second way of solving this problem using the concept of enthalpy that we introduced earlier. Remember, we said enthalpy H was just U plus PV. And so if we solve our energy equation for a constant pressure process, we get that Q is delta H. But delta H, when we invoke constant specific heats, is the mass times C sub P times delta T. I can find C sub P as Kr over K minus 1. So K is 1.35. R is the universal gas constant, 8.314, divided by the molecular weight of 32. That quotient having units of kilojoules per kilogram K. And again, K is 1.35. And I get C sub P is 1.002 kilojoules per kilogram K. Now, since I know Q is delta H, Q is also m C sub P delta T. I have a mass of 2 kilograms, a C sub P of 1.002, and I have T2 and T1, so I can readily solve this equation, and I get the heat transfer is 771.3 kilojoules, essentially the same answer I got in the prior solution, only this solution is somewhat simpler. So let's review all of the concepts that we used in solving this problem, things that were introduced during this problem solution. First, we introduced the concept of enthalpy or enthalpy, gave it a value of H, and it is equivalent to U plus PV. That's the internal energy plus the pressure times the volume. Internal energy we're familiar with. It's just the internal energy of the substance, and PV is the energy associated with pressure. We also introduced the concept of specific heats, C sub P and C sub V, and that sometimes we can assume that they're constant, even though C sub P and C sub V vary with temperature. If the temperature range of the process is not too great, we can assume that C sub P and C sub V are constant. And whenever we're given the specific heat ratio K, which is just the ratio of C sub P over C sub V, if K is given as a constant, then we can assume that C sub P and C sub V are constant for this process. Now, for an ideal gas, C sub B and C sub V are functions of K and R. So if we know K and we know what gas we're dealing with, we can calculate the gas constant. If it's an ideal gas, we can calculate C sub P and C sub V just by knowing K and R. Q is equal to the change in enthalpy in a constant pressure process for a closed system. Now, delta U and delta H are functions of C sub P and C sub V when we assume constant specific heats. And if we don't assume constant specific heats, then we're going to use table values. And delta U and delta H, which have units of energy, are just functions of specific internal energy and specific enthalpy. So we can always go to the tables and get accurate answers.